forgot to stop the recording, but yes, so working on empirical formula right now for the recording. Yes, so here we're going to take the mass of the metal oxide, subtract out the mass of the metal, because the reason the mass increased is because we added oxygen to it. So 1.95 minus 1.56. I still didn't find my calculator. Okay, I have to use this one. So 1.95, whoops, 1.95 minus 1.56. So 0.39 grams of oxygen. So the starting mass for oxygen, 0.39 grams. And then we're going to convert these into moles. So how do we convert copper from grams into moles?
The periodic table.
Yeah, periodic table, the molar mass of copper, 63.546. 63.546. And every mass on there, every mass on the periodic table, those numbers at the bottom, is going to be however many grams it is to have 1 mole of that compound. And then for oxygen, just do the same thing. So it's going to be, it should be consistent. I'm going to continue to use the 2 decimal places. So 16.00 grams of oxygen is 1 mole, oxygen. And then that'll give us the number of moles of each of those. So 1.56 divided by 63.546. So we're going to have 0.0245 moles of copper, and then 0.39 divided by 16. So it's going to be 0.0244 moles of oxygen. So now what? If we want to know the ratio.
Should we just multiply to get the whole number? But like maybe 10?
One step short.
Oh.
Yeah, I got to divide by the smaller number of moles first. So here, right, technically oxygen is smaller, but we know that both of these are going to end up to be almost exactly 1. So we'll divide by the smaller number of moles, which is oxygen, 0.0244, 0.0244. So this is going to be 0.0245 divided by 0.0244. So, right, 1.004, does that get cut off? Oh, it does get cut off, huh? It shouldn't be cut off, though. Huh. I don't know why that gets cut off. Oh, wait, no, I see it. Okay, well, I'll have to figure that out later. Unless it's just... I'll have to figure that out later. So it's 1.000 or 1.004. Right, so that's close enough to 1 at this point that we can just round it to 1. And so this will be 1 mole of copper, and then this is going to be exactly 1, and so it's going to be 1 mole of oxygen. So then the empirical formula for copper oxide is going to be Cu, This is one of the more formulaic calculations that we're going to do. Okay, but what if you want the molecular formula of a compound? If you want to find the molecular formula, it's always going to be a whole number multiple of the empirical formula. So when you calculate your empirical formula, you need to multiply all of the subscripts multiply them by 2, or multiply them by 3, or multiply them by 4, or right, any whole number times more will give you the molecular formula. Or, on occasion, it will be the same as the molecular formula, sometimes. So to figure out that number that we need to multiply, we have to already have the molar mass. So you'll be given the molar mass. Then you'll calculate an empirical formula for your compound. Then calculate the molar mass of the empirical formula. And it's the actual molar mass divided by the empirical molar mass. And that will tell you what n is. So how many, or what whole number you need to multiply your subscripts by. So just as a quick example, the empirical formula of hydrogen peroxide would be hydrogen and oxygen, and that would have a mass of 17.01 grams per mole, and that would be for the empirical.
So real quick, for this, you're adding both of them together to make one number, right? And then you're
Yeah.
going to multiply it by whatever is up there. Like, okay, so this is
Yeah.
easy to know. So you just took the 16 for oxygen and the 1.1 for hydrogen.
Yeah.
Made one number, and then you're going to multiply it.
Yeah, let me show you.
Okay.
You're on the right track. You're on the right track. But so I was going to say the 34.02 grams per mole would be the molar mass of the molecular formula. So if we take 34.02, divide that by our 17.01 grams per mole, that equals 2. Well, you can't even see the top of the calculator. So if we take the 34 divided by 17, that gives us 2, and then we can say, oh, in our empirical formula, we have to multiply the number of hydrogens by 2 and the number of oxygens by 2. So the molecular formula should be H2O2.
Well, where'd you get the 34 from?
That would be given.
Oh, okay.
Yeah. The molecular formula will be given.
Okay.
Yeah. So you're kind of doing the same thing in a different way, because if you take this 17.01, multiply that by 2, then you do get the molar mass that matches the molecular formula. And you could definitely do it that way if you can see it, or if you can see that this to that is multiplying by 2. If it's harder to see, taking 34 and dividing it by 17, or whatever the molecular molar mass is divided by the empirical, that'll tell you how many times bigger it is. And then you take your subscripts and multiply those. We'll do another example, though. Actually, I think we have 2 examples. So the empirical formula for fructose is CH2O, and its molar mass is 180 grams per mole. So what is the molecular formula? So the 2 things that we need, one is the molar mass of the molecular formula. So we're given that. So I'll write that as molecular equals 180.2 grams per mole. And that's representing what the actual molecule is. Then we also need the empirical molar mass. And we're going to have to calculate that from the empirical formula. So we'll just take the fact that we have carbon, hydrogen, and oxygen. There's 1 carbon, 2 hydrogens, 1 oxygen, and then multiply those by the molar masses of the individual elements. And so this will be 30.03. So 30.03, that's the to calculate the empirical formula, molar mass. And then we take the molecular formula divided by the empirical. And that's going to be 180.2 divided by 30.03. And that comes out to, oh no, that's not what I wanted. This is why I don't usually use the calculator on the iPad. It's very glitchy. And that equals 6. It was like 6.000, right? So this number equals n. And so we're going to take our CH2O. We're going to multiply each of the subscripts by 6. So for carbon, that's going to be C6, and then H12O6. So it'd be the molecular formula of fructose. Ah, I found it. All right, so we can. Can you see the calculator now? Almost. Let's do. Never mind. It just doesn't quite work. The aspect ratio of the screen is different than that on the iPad, so it's like, it's just not going to work. Okay, does that make sense? It's really, we're trying to just figure out how many times bigger, how many more molecules we need to add. And it's going to be a whole number and a whole number ratio. It'll always be a whole number. Yeah, you'll never do this calculation for n and get like 1.5. Because you can't have half a molecule. So butane, the compound containing carbon and hydrogen, it's used as fuel in butane lighters. Its empirical formula is C2H5. Its molar mass is 58.12 grams per mole. And we're going to find its molecular formula. So kind of the same thing here. The molar mass of the molecular formula is 58.12 grams per mole. And we're also going to need the empirical formula molar mass. So this will be carbon, hydrogen, 2 carbons, 5 hydrogens.
Aren't we trying to get the molecular formula?
What?
Aren't we trying to get the molecular formula?
Yes. So this is the empirical formula.
But the one on top of empirical is molecular.
The what?
In the board you wrote molecular and then 58.
Oh, yeah, the wording here is a little bit confusing. It's is referring to the
Mass.
molecular formula. Yeah, so the formula of butane is actually 58.12 grams. And we'll see that the C2H5 here is going to give us a smaller number. (24.01), 5.05. So 29.09 grams per mole. 29.09 grams per mole. Oh, I don't know why. Must be a little bit dyslexic this morning.
It would be 0.07 because the carbon.
Oh, yeah, that is that too.
This is why I miss my calculator. Thank you. And I need to change this one. Okay, cool. Now we're on track. So now what do we do?
So then you divide the 58.12 by 29.07,
Yep.
and it's 1.9993.
That sounds right. Calculator, can you scooch? 58.12 divided by 29.07, 1.9993. So yeah, so that's close enough to 2. You can very, very, very comfortably call that 2. But we're not quite done yet, because now we got to take our C2H5, and we're going to multiply both of those by 2. So this is going to be C4H10, and that's the molecular formula for butane.
Did you say divide or multiply?
I think I said multiply. I meant to say multiply. Cool. So that is chapter 6.